Hi everyone. In this lesson, we will go over two applications involving integration, and one of them is called exponential growth or decay, and the other one is called Newton's law of cooling. And along the way, we'll also learn a technique called how to solve simple separable differential equations. So let's get started with the exponential growth model and how we can use integration to understand that topic. So, you may have seen this in college algebra, like A equals P times e to the RT. So there the formula was handed to us. We didn't question it, we just started using it. It was the way money grows in a bank, and we assumed it would be an exponential growth pattern. But where does this formula come from? So now that we understand calculus and many tips about calculus, many techniques, we're able to understand that formula deeper and where it comes from. We're going to derive it in what follows. So the basic assumption is this: if a quantity grows at a rate proportional to the existing amount, then the growth is exponential. So let's think about this for a minute. If a quantity grows at a rate proportional to the existing amount. Now think about how money grows in a bank, right? You put the money in there, let's say it grows at 5%. So the more money you have, the more that interest you're going to earn on that money. So it does indeed seem to grow at a rate that is proportional to the existing amount, how much you have invested, right? Also think about the way, for example, diseases spread. It's another example of a situation where the rate of growth will grow proportional to the existing amount, because think about it, depending on how many people are infected, the larger that number is, the more the disease is going to spread, right? So it's going to spread at a rate proportional to the number of people currently infected with the disease. So there are many examples like that. So this is not an unrealistic assumption that a quantity may grow at a rate proportional to the existing amount. And here's the interesting thing. If you make that simple assumption, we're going to show that then the growth is automatically exponential. Now, in mathematical terms, this is what we're saying, okay? If the rate of growth is proportional to the existing amount. So let's say the existing amount is represented by y of t. This is our population size at any given time t. So the rate of growth would be the derivative, right? dy dt. And proportional in mathematics means a constant times, okay? So if dy dt, the rate of growth, is proportional, meaning a constant times the existing amount, which is the quantity itself, which is y, the function y, what we're saying is then we're going to be able to show that y is a constant times e to the kt, meaning that y is an exponential function, therefore the growth is following an exponential pattern. Okay, now let's see how we can prove this by using this technique called separable differential equations. So once again, our basic assumption is this, that dy dt equals k times y. And so all we have to do is now to solve this equation for y, okay? It is called a differential equation because you have a derivative on one, within the equation you have an equal sign, so you're going to try to get rid of the derivatives and to try to get to the bottom line, the function itself. And the way we're going to do this is we're going to separate the variables, first by placing the y's on the left-hand side and the other variable, the t's, on the right-hand side. So let's do that. So to begin with, I'm going to do something unusual perhaps. I'm going to multiply both sides by dt. So this is our original assumption, multiply both sides by dt. So now we have dy equals k times y times dt. And I want to collect the y's on the left-hand side. So let me divide both sides by y. So over here they're going to cancel. Over here you're going to have dy over y equals k times dt. Okay. And the next step, to get rid of a derivative, we're going to integrate both sides. Okay, so integrate this side, integrate that side with respect to the corresponding variable on each side. So that's what we're doing right now. So what is the integral of 1 over y dy? So this is something we did not know in college algebra, but you know at this point in the calculus class, right? So integral of 1 over y dy, I think you all know this by now, right? It's ln of the absolute value of y. And so here I'm showing just that step, but left-hand side is ln of the absolute value of y. And what about the integral of k dt? Now it looks like maybe you have two variables, but k is the constant of proportionality. So think of it like phi. What is the integral of phi with respect to t? If you said 5t, you're absolutely correct. So if it is k, it'll be kt. Now, of course, we always had the plus c at the end there, so kt plus c. At this point, we can make the assumption that many times, we're dealing with positive quantities like the population size will be positive. So we can drop the absolute value if there need be in our cases. And to solve this equation, we're going to apply property of logs. Basically, what we do is like we raise this side e to the ln y and this side e to the kt plus c. That way we're going to try to get rid of the logarithm because e to the ln, they cancel each other, right? So on the left side, we're going to have y. And again, remember, I'm dropping the absolute values because I'm assuming the y quantity is already positive. I'll do it in the next step. So absolute value of y equals e to the kt plus c. And there is a way to simplify the right-hand side. So this can be written as e to the kt times e to the c. And you may wonder, how is that possible? How did you go from this quantity to this product? Well, I want you to think about backwards for a minute. If you were multiplying these two quantities, you would be adding the exponents, right? Because you have the same base. So this would turn out to be so here you would add the exponents, you'll have basically this expression that you see on the left-hand side. So here we applied a little trick. We broke it apart as e to the kt times e to the c. And furthermore, you can write e to the c as another constant, such as a capital letter C. So therefore, we can now, in addition, again, using y as a positive quantity, drop the absolute value, we can say y is equal to the right-hand side, which is e to the kt times, so we're calling this entire quantity capital letter, let's say C, another constant C. So C times e to the kt, that's all we have. So remember, what was our initial assumption? The growth rate is proportional to the existing amount. And what is our final result? That the function that represents the population at any given time is an exponential function. So this will be very important in some of the examples that we solve, but now you also understand how they came up with like a equals p times e to the rt, because this is practically the same thing. Instead of y you have an a, instead of c you have p, and instead of k you have r, but it's really the same type of a situation. And in the next segment, we're going to take a look at some examples using the exponential growth function, something like y equals c times e to the kt.